Hi, in this quick presentation, I'd like to give you an overview over our paper, the Vector Model on Subcritical Inhomogeneous Random Graphs. And this is joint work with John Fernley, who is a PhD student here in Bath. We're looking at the Vector Model, and the Vector Model is one of the classical models for modeling the spread of two opinions across a network. Each vertex can have two opinions, 0 or 1. And at the beginning, we let each voter independently chooses its opinion. And then the dynamics are as follows. Each vertex updates its opinion at a rate degree to the power theta, where the degree is the number of neighbors in the underlying graph, and chooses one of its neighbors uniformly and just copies its neighbor's opinion. And what is a little bit special about our model is this parameter theta here, and we'll call this a temperature parameter because it determines how the voter model is influenced by the underlying graph. Standard choice is theta is equal to 0, so you're updating at rate 1, and theta is equal to 1, so that means each neighbor has pushed its opinion onto vertex v at rate 1. But we really like to keep this parameter because it allows us to play around a bit and see how the underlying geometry of the graph influences the dynamics. And for finite graphs, the main questions in vector models is how long does it take to reach consensus? So how long does it take until everyone in the same campaign has the same opinion? Obviously, different components cannot interact, so in the end, they might end up with different opinions, but within a component, eventually consensus is reached, and the question is, how long does that take? As the underlying graph, we're interested in inhomogeneous random graphs, and the reason for that is that inhomogeneous random graphs share a lot of the features of real-life networks, and this particular variation is due to Chang and Liu. So vertices are labeled 1 up to n, independently for each I and j. I and j are connected with the probability pij, which is inverse proportional to I to the gamma times j to the gamma. The gamma is some parameter, and these parameters beta and gamma are chosen such that vertex I has an average by beta times n over I to the power gamma neighbors. So you see that vertex 1, for example, has beta times n to the gamma neighbors, whereas vertex n has an average beta. So there's a lot of inhomogeneity in the system, and parameter beta tells you how many edges there are on average in the system, whereas gamma determines how inhomogeneous the graph is. So these models have been studied a lot over the last 20 years, and in particular it's known that the model is supercritical, so that means it has a giant component. So the largest component in the system is of order n, if and only if beta plus 2 gamma is strictly greater than 1. And the important thing is that these models are known to be scale-free. By that I mean that if you take a uniformly chosen vertex, then that has degree k with probability that decays like k to the minus 1 plus 1 over gamma. And this quantity here is typically known as the tail exponent tau. So again, that's one of the features that you can observe in real-life networks. To give you an idea of what these models look like, here are a few simulations. And what we would be interested in, which is a little bit unusual, is we're interested in subcritical random graphs. So we're assuming that beta plus 2 gamma is strictly less than 1. And if you draw these random graphs, it looks a little bit like this. And in this simulation, I've excluded all the vertices that have degree 0, so they're isolated, because for our purposes of the Vector model, they're not interesting at all. So you see for small n, you've got a lot of components here, and they're all reasonably small. And so if you increase n, you'll still keep lots and lots of components, but the components start to look a lot more interesting. So you can really see here that you have an inhomogeneous random graph, and you see this self-similar structure appear. This is just a component of vertex 1, and you have to imagine that there are lots of other components, but it's going to be hard to simulate. Okay, so what's our result? Our result is about the consensus time. So recall that's the first time when each component has one opinion. And so we take a subcritical inhomogeneous random graph Gn. So we consider a voter model with parameter theta, where you may recall that means each vertex updates at rate degree to the power theta, and with starting with I de Bernoulli initial conditions. So each vertex takes opinion 1 with probability u, and otherwise it takes opinion 0. And our main result says that the expected consensus time, where we condition here on the random graph, so this is a random quantity. This random quantity is of order n to the power some constant c. And this constant c depends on the parameters gamma and theta. And our notation here means this log n means that we allow multiplicative factors of log n to some power in there as well, but we also have upper and lower bounds, and they hold in probability. And the interesting thing is now this exponent c here. So if theta is greater than 1, then you get c is equal to gamma, which is maybe what you expect because n to the power gamma is the size of the largest component. But if you consider smaller theta, then something interesting happens. And if I plot this function for a fixed gamma, in this case gamma is equal to a third, you see the following. So for small theta, you have a decreasing function, then it's a constant for a while, then it increases again in theta, and then it stays constant again, theta greater than 1. So you see there is something non-linear going on here in some sense, and the underlying geometry of this forest of all these different components really plays a role. And the dominant contribution in these exponents does not always come from the largest component, which would be the one corresponding to vertex 1. If theta is strictly less than 1 over 2 minus 2 gamma, then a double star component further down in the block takes longer than component vertex 1 to reach consensus. And in our paper, we'll also look at a model where the voters discuss their opinions and then agree on one opinion. We also have the same full picture, but the dynamics are slightly different. And how do we prove this? Well, we use the well-known duality for the voter model. And this is a duality to the system of coalescent random walkers. You can sort of imagine if you let the voter model run forwards in time, then you get these coalescent random walkers by taking opinions and tracing back where they have come from. And in particular, if you want to know about the consensus time, it's absolutely essential to understand how long does it take for 2 independent random walkers to meet. And again, that very much depends on the geometry of the underlying graph. And so we have to develop quite a detailed understanding of these random graphs to then pull out these results about the random walkers and then about the voter model. And as you may imagine, there has been a lot of previous work, in particular, directly in his book has an overview of some results, but there are other results since then. There's also a paper by Sud, Antal, and Redner who look at a mean field analysis of this question. But just to emphasize, our model is sort of a fixed random graph, and then look at the dynamics. That's very different from a mean field analysis, and you don't get the same answers, especially for these subcritical inhomogeneous random graphs, at least not in all cases. Also, general results for random walkers and random graphs are very much model dependent, so you can't just pull out these standard techniques. You really have to work with your model. So thank you very much for listening to this presentation. If you want to read more, and I hope you do, please have a look at our preprints. It's on the archive, and come and ask me questions in the question section. Thank you very much.